This is lecture 5. So in the previous lecture we briefly discussed about uh, the how to transmit a signal without how to transmit a baseband signal effectively from multiple users without really uh, creating a mess, right? Without really creating a mess of uh, all the users using the same frequency band simultaneously. And we saw that the effective way of doing that uh, was to transform the frequency band from one to another and maybe give each user his or her own frequency slot to transmit. So that way each one of us have a has a specific frequency band which I can use to transmit my signal, and we will not step into each other's doors, right? So that's all good, but now in this lecture we'll switch our interest and turn our interest towards the receiver part, where we would like to see what happens if how does a receiver know, right? How does a receiver know what to expect? And when I know what to expect, right, as a receiver, what are the steps that I should be taking, right? So let's get started. So now we are concentrating on the receiver side of it, right? So I'm a user, I'm a receiver. So what am I receiving? I am essentially, there is an antenna connected. There is an antenna connected to any wireless receiver. There are signals coming in, and signals are coming in at not only from the user of interest, but it is also coming in from all the other transmitters that are probably around, right? So, but the only thing that I know is, let's say I know a priori that I am supposed to listen to a particular channel. Okay, so if I am supposed to receive to a particular channel, which means that a priori I know that I should be tuning in to some particular frequency, and let me call it omega LO1, right? So let me just call it omega LO, right? So let's say we know a priori that the frequency of interest is around omega LO. Now, one definition that I missed in the previous lecture was what is meant by LO. So LO stands for local oscillator. So why do we call it a local oscillator? If I take you back to the previous lecture, so what did we do? We essentially took the baseband signal VBB, which had probably a bandwidth of a VB or omega BB, and we multiplied it with a high frequency clock, right? With some sinusoidal signal which had a different frequency, and we called it omega LO. This we called it cosine of omega LOT. What is essentially this? This is a known signal, a known periodic signal, right? So, and this known periodic signal is a part of the system, right? It's a part of the system, it's a known part of the system. Note that this is an user input, this VBB is an user input which can randomly change, right? It's an input, but this is a known clocking signal. Now, if something is known a priori, I can generate it locally, right? So, for example, each of your cell phones have a crystal inside, and that from the crystal oscillator, we generate this clock. Hence, the term local oscillator. Okay. So, the popular terminology is to simply say LO. As the course progresses, we'll just shift to the popular terminology. But for the time being, we'll restrict ourselves and say that your output is essentially uh, omega LO plus omega BB, and or let me just say omega LO plus minus omega BB, right? Because your omega BB is probably both sided, right? Okay. Uh, so now we coming back to whatever we were discussing, we are expecting signals from at the frequency of omega LO, right? So uh, so my signal is, if I now draw a spectrum, so let me go to the next page. So if I draw a spectrum at the input of the receiver, what am I expecting? I am expecting signals around omega LO. I'm not drawing the negative frequency, but it is assumed that the negative frequency component also exists, right? So to make it slightly cleaner, okay. So this is what we are interested in. Just to take an example, let's say if omega LO is 2 pi times 1 gigahertz, that is FLO is 1 gigahertz, okay. And typical example of omega BB, if it's a voice signal, it's few kilohertz. If it's a radio signal, if it's a video signal, few megahertz. I'll just say it's approximately 2 pi times 1 megahertz, let's say. This is just to show you the typical differences between the LO frequency and omega BB and the baseband frequencies, right? Okay. So now I know that my signal is around omega LO. So now the signal comes in to the input of my chip. So what should I do? Note that what is the information? The information is only around that narrow band of plus minus omega BB, right? So this is the information exists only in the narrow band of plus minus omega BB around omega LO. So if that is the case, there is no point for me to take in that 1 gigahertz signal when my information is only at 1 megahertz, right? So what should I do? Ideally, since my information is only around omega BB, I can translate this signal back around DC, right? I can translate the signal back around DC. So what is the goal? The goal is to translate this guy back around DC. And if I can do that, then I can peacefully process this signal, because this is now a much lower frequency component, lower frequency signal to handle. Now, inherent in that argument is the assumption that it is much easier to handle low frequency signals than high frequency signals, right? So without going into the details of why, I would like to draw your experiences of basic analog circuit courses, where you must have seen that at high frequencies there are a lot of capacitive effects, phase lag effects, instability effect that comes into picture, which makes design at high frequencies quite challenging, right? However, if the frequency reduces, then there are a lot of other circuit techniques that can be used to process analog signals effectively. And note that ultimately everything has to be digitized, because things are stored in a digital format, right? So it is always better to have a signal which has a limited bandwidth before I feed it to an ADC, right? So ultimately, because the ADC also has to operate with otherwise has to operate with a very high frequency clock, right? Okay, fine. So that is those are very system level information. If you are not following me right at this point of time, don't bother. As the course progresses, things will become clearer and clearer. Okay, fine. So let's proceed. So the goal is now to convert this signal back around DC, right? Because the initial signal was also around DC. So what should I do? So frequency, there is only one way of translating frequency that we have learned so far in this course, and that is by mixing or multiplying, right? Multiplying in RF parlance is called mixing, so we'll also call mixing. So I can multiply this guy with 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 the same clock around omega LO, right? So if I multiply it around omega LO, what's going to happen? So this input is omega LO plus minus omega BB. So the output will become, so the output will be at what? So note that if you go back to the previous lecture, so let me just take one frequency at a time. Let's say omega LO plus omega BB. So your output will be omega LO plus omega BB and shifted to the left and shifted to the right, right? So essentially the signals that the frequency components that I will get at the output will be 2 omega LO plus omega BB, and I am also going to get omega LO plus omega BB minus omega BB, so I am also going to get omega LO, right? Okay. Note that note that similar things are going to happen for the negative frequency also, right? I'm just omitting the negative frequency because essentially everything flips around, right? Okay. So now if I again take some numbers, then what do you see? What is this 2 omega LO plus omega BB? So essentially I am getting two sinusoids, right? So essentially I am getting, how am I getting two sinusoids? I am getting cos omega LOT times cos omega LO plus omega BBT. So this becomes, if I say 2 cos cosine, just to make life simpler, I know that this identity is essentially nothing but cosine 2 omega LO plus omega BB T plus cosine omega LO, right? So I am getting two cosinusoids, so basically signals of 2 omega LO plus omega BB and omega LO. Now, sorry, I made a mistake here. This should be around omega BB, right? So what is the signal of interest between these two? Clearly, omega BB is a frequency of interest, and the good thing is now omega BB or FBB is around 1 megahertz, and 2 omega LO plus omega BB is around 2 gigahertz. So they are like far separated away. I mean, they're far off in terms of frequency, right? So now, why do I say it's a good thing or a bad thing? So note that this signal has this node, the output node now has a high frequency component and the low frequency component, out of which the high frequency component is undesirable and the low frequency component is desirable, because I'm anyway getting the signal information in the low frequency component. I do not want to handle high frequency component, so I need to discard it. So what should I do to discard it? A high frequency component and keep the low frequency one? Basically we need to use a low pass filter, right? So let's use a low pass filter. So let's use a low pass filter, fine. And low pass filter, what should be the cutoff frequency of the low pass filter? It should be sufficiently small so that it rejects the component at 2 omega LO, right? So the bandwidth has to be much smaller than 2 omega LO. 2 omega LO and 2 omega BB are plus 2 omega BB doesn't really make a difference, but it has to be greater than omega BB, right? Okay, fine. So it's a base bandwidth. Okay. So now at the output, what do I get then? Output, I can get a pristine omega BB signal, which is something that we started off with in the transmitter side, right? Okay, fine. So this is a very rudimentary receiver architecture, which seems to be doing our job. Okay, but not so fast, because remember, what did I tell you? We are not the only receiver. We are not, our receiver is not only receiving signal from our band of interest, right, or our, not even our channel of interest, uh, uh, but it is receiving signals from all neighboring bands. Okay, so for example, yeah, if I take, I mean, the GSM standards, then without getting into exact frequency bands, we know that your receiver band and the transmitter band are centered around somewhere around 900 megahertz, and the distance between the, or the frequency separation between the receiver band and the transmitter band is approximately 20 megahertz, right? Which essentially means that I am receiving, I am holding a cell phone, I am receiving something at say 910 megahertz or something, and somebody is transmitting sitting next to me at 930 megahertz. Okay, and but maybe I am expecting a signal from maybe 935 megahertz, right? The key point to appreciate here is that you are going to get signal, like it or not, from all different channels, all different bands, right? And they may be very close to your own reception band of omega L. Okay. So now here I would like to make a distinction between a band and a channel, because we are going to use these terms quite often, right? So I have been using these terms, bands and channels. I have started to use these terms, before getting before I start using this more often. Let me just also make a distinction between what do I mean between a channel and a band. So as it turns out, in a radio receiver, this is a very protocol level decision, but for a circuit designer also we need to be aware of this. A channel is essentially a small frequency. A channel is, you can think of a set of frequencies which form a channel and set of channels which form a band. Okay, so it's typically a small range of frequencies form a channel, and a channel is generally fixed for a user when the communication is on, right? So that's, nothing is fixed for a user, but it's generally fixed for a user when nothing is fixed for a user permanently, but when the communication protocol is, when the somebody is making a call, uh, obviously I'll be taking up some part of the spectrum, and that minimum amount of spectrum that I'm supposed to take up is, you can think of it as a channel, right? This is what a channel is. And a band is essentially a continuous set of channels. Okay, so sometimes you will hear that maybe a GSM band has it has around 35 megahertz of uh, I mean, a particular band has 35 megahertz, a particular band has 10 megahertz, a particular band has 20 megahertz. That does not mean that one user who is using that particular band is going to get that entire 20 megahertz or 40 megahertz or 30 megahertz. It essentially means that that band has been assigned to for a particular protocol. Now, when I am using as a service provider, when I am giving service to a user, so what I would like to do is, I would like to pack in as much user as possible within the band. So while during the transmission or reception, I subdivide the bands into smaller channels, right? And typically the transmission bands and the receiver bands, the transmission bands and receiver bands are separated by some sort of a stopgap, right? So as far as design is concerned, you need to understand that if I draw it in the spectrum, if this is F, so you can think of a continuous spectrum. This, let's say I call this receive band. RX stands for receiver. Let's say I call the receiver band, and TX stands for a transmitter. So let's say I call this a transmitter band. So there will be a band for dedicated for transmission and reception, but each transmission and reception bands are also divided into channels, right? So a transmitter band will be divided into channels. Similarly, a receiver band will also be divided into channels. And very crudely, when you are making a call, you are probably sitting in one of the channels, right? So you are probably taking this amount of spectra when you are in receiver, and maybe taking this amount of spectra when you are transmitting. Okay, and when I am saying I am deciding this omega LO, right? All I am saying is that your omega LO is probably omega LO essentially is decided by wherever your band or the channel is, right? So this is your omega LO, right? So if you are now obviously you are going to have a separate omega LO for receiver and separate omega LO for a transmitter. So you will have omega LO RX, you are going to have omega LO EX. Now the obvious question that can come to your mind is that just now I said that I am expecting something at some omega LO, but here it looks like I am transmitting at a different frequency, I am receiving at a different frequency. That's, even though it appears so, but it's actually not the problem, because we do not communicate between one cell phone to another cell phone directly, right? It goes from our cell phone to a tower, and then tower to the receiver, right? So that the frequency change happens in the tower, right? So we are all good, right? So basically there is an intermediary who ensures that this handshaking is this communication goes on without any problem. Okay, so that was a slight amount of detour, which I hope will be useful, and I hope I didn't confuse you more. I mean, the intention was not to confuse, but the intention was to ensure that things go well. I mean, things get cleared, but I mean, hopefully that I was able to convey. Okay, so now, so where were we? We wanted to. What I was trying to motivate here is that, so even though in the RX band you are sitting around some omega LO, you are receiving at this from this band, you are receiving from this band, you are receiving from this band. Not only that, you are also seeing transmitter bands, right? Because you are also seeing outputs from the transmitter bands which are impinging on your antenna, right? Imagine a situation where I and my friend are sitting next to each other, and I am making a call where I am receiving information from somewhere, and my friend who is sitting next to me is making a call to somebody else. So we are not communicating over cell phone, but we are not communicating with each other via cell phone. But what is happening? So the friend of mine is directly. So let me now draw it here. So let's say this is me. So I am sitting here and I am receiving. This is my friend who also has an antenna who is transmitting. And this is supposed to go to a base station. This is supposed to go to some tower, right? And this tower is supposed to send signals to me, right? So this is supposed to go there, and I am supposed to get signals from tower from some other band, right? From somebody else. But since we are sitting next to each other, this guy is also coming here directly, right? So now what's the problem? The problem is if I go back to the previous page, the problem is I am getting signals from omega LO plus omega BB, and I am also getting signals from omega LO maybe plus some omega, I will say INT. INT stands for interferer. Okay, so I am let me use a more standard term. I am also getting a signal from omega OOB. OOB stands for out of band. It's an out of band blocker. So I am getting signals from, this is omega LO plus, with respect to, if I compare with respect to omega BB, I am getting a signal at omega LO plus some delta omega, which is close to omega LO but an unintended signal. Okay. So now if I am getting that, what's going to happen? This signal is again going to come in, right? And it is again going to get mixed with omega LO, right? It is going to get mixed with omega LO, and it's going to come to the input of the low pass filter, and I am going to get some other baseband information also. But the problem is it's not like I'm getting another baseband information is the problem, but the problem is the strength of the signal that I'm supposed to receive from the tower, which is probably 1 kilometer away, and the strength of the signal that I'm receiving directly from my friend who is sitting next to me can be quite different, right? So as it turns out, this signal that I am supposed to receive, maybe I should change the colors, because this is one is intended, other is unintended. This is intended and this is unintended. So this, as it turns out, this can be the intended signal strength can be of the order of as low as minus 100 dBm to minus 90 dBm. Right? And the signal that I am receiving directly, or not the signal, the interferer that I am receiving directly from my friend can be of the order of 20 to 30 dBm. Right? So you see that there is a difference of 120 dBm, right? That's a huge difference to take care, right? So it's of the magnitude of how much? 10 power. The difference is of 100 dBm is essentially 10 power 10, right? So you see the difference in magnitude of power that you are getting here is huge. So I have a mixer here. So we are getting signals of extreme variation of amplitude. Extreme with the exclamation mark, right? Because it's and you are getting it simultaneously. And the weird thing is that I would expect to process the weaker signal and not process the stronger signal, right? Now you might say that, hey, I can use I can use a low pass filter. Anyway, I am having a low pass filter here. That low pass filter should be able to knock it off, but not so fast. Note that your mixer, I have not talked about this till now, but your mixer is also made up of some sort of transistors. The moment you have something which is made up of transistors, from again drawing from your experience in analog circuits, I would like to point out that transistors are nonlinear devices, right? So they can, if the transistors are not biased properly, they can saturate out, right? And they can lead to a lot of distorted output signals, right? So which essentially means that we have to take care that large amplitude signals, especially when they are unwanted large amplitude signals, they do not come in. So if we have to do that, we have to put some sort of filtering before the mixer, right? And that filtering cannot be done with anything which constitutes a transistor, right? So that has to be done in the fully passive way, and as it turns out, that is done with something which some sort of passive filtering, But the key specification of the passive filter is not only that it has to be very linear, it also should have extremely sharp roll off. It also should have extremely sharp frequency roll off, right? So what I mean by that, so the example that I took here, right? So of this separation of the RX and the TX band. So typically I can give you an example. So in GSM, in GSM, the TX band, the TX and RX bands are separated by approximately 20 megahertz and located around 1 gigahertz, right? So why is this information important? It's important because now if I sketch my TX band, or if I sketch the GSM band, I don't need the y-axis for the time being. What am I saying? I am saying that you have an RX band here and you have a TX band there, right? And I know that the TX power is generally, the transmission power is generally much higher because you are transmitting at the top of your voice, or other way to say is that uh, your cell phone is transmitting the maximum power, so that the power signal actually reaches the tower, which is probably 1 kilometer away, and but the RX is getting a signal from some other tower which is another 1 kilometer away, right? So your RX is getting a very weak signal, but the TX is transmitting a very strong signal. So generally your TX will have a extremely strong this is power, right? This is power. And your RX is going to have a very weak power, and this difference can be as high as 100 dBm. Okay, so now the thing is, so this is, let's say, I'm just taking an example, it's 900 something, but let's keep it simple. So this is 1 gigahertz, and this spacing is 20 megahertz. So in order to ensure that this TX signal does not come and saturate out your receiver, you must have a filter, a band pass filter around this TX band, so that, or rather around the RX band, so that it knocks off the TX as much as possible, right? So you would require a band pass filter so that it knocks off the TX as much as possible. And the specification typically that is required is, if you are transmitting something of the order of 20 to 30 dBm, you would at least want to lower it by around 30 to 40 dBm, 30 to 40 dB, so that your receiver can handle the lowered power. Okay, so which essentially means that general specification is this band pass filter needs to have approximately 30 to 40 dB attenuation between RX and TX. That is, within the 20 megahertz band, it has to drop by 40 dB. Now that is extremely sharp amount of roll off, and that unfortunately is not very trivial to design in an on-chip way, and that is why till now most of the radio receivers that we see use a separate off-chip filter. It's an acoustic filter, and it's called a surface acoustic wave filter or a SAW filter upfront, right? So right after the antenna there is typically a SAW filter. So I'll just put a SAW filter. It's called a SAW, surface acoustic wave. So we typically put a SAW filter which is centered around the center frequency of the received band, right? So this will be centered around, I mean, if I have to use this topology, then this has to be omega LO, where omega LO is center frequency of band, or let me just say Rx. It can be band or channel depending upon the protocol, but let's keep it generic, right? Okay. So now you have this, right? So now you have this, and let's say now our mixer can handle I mean minus 10 or minus 20 dBm of transmit power. Let's assume it can handle, but you have the intended signal is still very weak. Intended signal is approximately of the order of minus 90 to minus 100 dBm, right? So your intended signal, your Rx signal, is of the order of minus 100 dBm, right? So you can you can do a quick calculation to figure out what does minus 100 dBm translate to in terms of signal. In that calculation, what you can do is you can, so DIY, do it yourself. That is, what does minus 100 dBm power translate to in amplitude, assuming resistance is equal to 50 ohm. Now I have not till now talked about any resistance requirement, right? It will come in the future lectures, but for the time being, assume that there is a reference resistance of 50 ohm, and this 100 dBm power is referred to that 50 ohm, that is 50, V squared over 2R, where V is the amplitude of the signal, is equal to some power then expressed in dBm, right? So if that is the case, you will get a fair idea of the level of the signal that we are dealing with. Okay, what's the problem? What's the problem of dealing with a very low signal, right? The usual problem is, ultimately I would like to take this signal and give it to an ADC, right? Because I want to get bits out, right? So now ADC also needs typically ADC also have discrete quantized levels, right? So ADC also needs some input of some range. You cannot have extremely small amount of input, then ADC will always give out 0 0 0 0, right? So then you might say that, hey, I can always take this signal and amplify it. Sure, I can do that. I can always amplify it, but in principle, I can always keep amplifying any signal, right? I can always keep, even if it's like minus 1000 dBm, I should be able to amplify in principle, right? But we all know that's not the case. The reason that is not the case is because ultimately, fundamentally, each device that we have is also limited by some intrinsic noise. So each device, noise will be something that we'll also talk about in future lectures in quite amount of detail. But for the time being, again, be cognizant of the fact that each device, each active device will produce some inherent noise, right? Regardless whether you transmit anything or not, it's sitting doing nothing. But if you observe the output, you will see some wiggling in the oscilloscope or in the spectrum analyzer, wherever. We'll never see perfect zero, and that is because there is some amount of noise that any active device throws out. Now, if the signal that you are processing is weaker than the noise that your amplifier is generating, then you have big problems, right? So that is why having only an amplifier is not a solution. You need to have something which not only amplifies your signal but also does not add too much of noise, right? So that is why at a very system level we can assume that there is an amplifier which needs to be added before your signal goes in, and we call this typically a low noise amplifier. Okay, so after the SAW filter, so this is a SAW filter. Typically a low noise amplifier is interfaced with the SAW filter, which gains up the signal to some extent, right? And then we give it to our mixer, and then there is a low pass filter, right? Okay,